All right, in this module, let's talk about electronic defects. And we're going to start by considering the kind of absolute zero case. So at 0K. So at 0K, all electrons are localized to the nuclei. And what we call free electrons, right, those in the conduction band, and the resulting holes do not exist. However, we're really never at 0K, right? So we really care about elevated temperatures. So at elevated temperatures, we have lattice vibrations, and that knocks loose some electrons to the conduction band. And if we knock loose electrons to the conduction band, we leave behind electron holes. And those are in the valence band. So this is an example of what we call an intrinsic semiconductor. So it's not from any dopants added or impurities. It's from within, intrinsic to the material, just based on really temperature, right? And so we have the formation of an electron hole pair, as we term it. And so the reaction for this intrinsic semiconductor can be written as, null, or the perfect crystal, and it goes to, we're creating we're creating an electron in the conduction band and leaving behind electron holes. So we can write that as, again, lowercase e, and then we use our charge, so the dash for negative, plus a hole, which is lowercase h, and then a dot for the plus charge. Right? So this is our reaction for an intrinsic electronic defect, or from an intrinsic semiconductor. Right? So this is what happens in a semiconductor when we create an electron hole pair. So you can see that this will be closely related to the temperature, right? The increasing the temperature would increase the number of these defects, and that's related to the energy that's required. And so we can actually write this in terms of the numbers. So electrons, the number of those electrons is frequently referred to as N, or in an N-type semiconductor. And then P for P-type, and that's related to the number of holes. And so basically we have the product of the number of electrons and the number of holes divided by the total number of sites in the valence band, and this is known as the density of states. And then we have the density of states for the conduction band, or the number of sites there. And this is all equal to an exponential of negative in energy, and this is Eg, divided by KT. And this is the same as our mass action expression for this intrinsic semiconductor. So let me just go through some of the variables here and kind of show you this equation real quickly. So N is the number of free electrons. And this is per unit volume. P is the number of electron holes. And then same thing per unit volume. And the these are the density of states. For valence band. And the same thing for the conduction band. And the last thing here, we've already addressed K and T, right? Boltzmann's constant and temperature. And then this EG, this is the energy it must overcome. This is known as the band gap, right? You may have heard that before. And this is the energy required to go from the valence to the conduction band, right? So that's what the energy required to liberate that electron, leave behind an electron hole. So from here, though, obviously these are our numbers of electron holes, but the density of states, we kind of need to address that point. So let me go ahead and show you how we calculate those quantities. So for the conduction band, this is equal to 2 times 2 pi m e star, and again I'll address these after I write it down, times kT over h squared, and this is all to the 3/2 power. And then we have a similar expression for the valence band, and the mh instead of me, this is star times kT over h squared again, and this is to the 3/2. So let's go over the kind of the new terms that we're talking about here. So this is me star, that's what you see up here. This is known as the effective mass of an electron. So in particular materials, we have an effective mass because it refers to kind of the speed it moves in that material. And the same thing, we have an effective mass of a hole, even though that's kind of doesn't really make a lot of sense, but it's talking about how quickly it travels. And so this is an effective mass of an electron hole. We also have Planck's constant, h, and this is 6.626 times 10 to the minus 34, and that has units of meters squared, kilogram per second. So if we kind of think back to statistical mechanics that we talked about for Boltzmann's equation, this density of states you can kind of think of this as the number of sites or energy states that we have for our electrons or electron holes, right? So in the conduction band, and how many sites or energy states we have in the valence band. Also, one last thing we need to kind of define here is the concentrations. So we can talk about the electron or electron hole concentrations as N, and so again we use the site fraction here, the square brackets, is equal to the number of electrons per unit volume, and then the number or the density of states for the conduction band is also in those same units, so number per unit volume. And so again, this turns out to be a site fraction, and then we can talk about P as the same thing. And so the reason we kind of define it like that is because if we go back up to this expression here, then this becomes site fraction of electron, site fraction of electron holes equals this exponential term that we have. And again, if we write the mass action expression, this is the same thing as what we would get, right? The equilibrium constant. And we put I for intrinsic electronic defects. So this is kind of what we're working with. So in the next module, we'll go through an example of how we can calculate these numbers.